Today we're looking at the disk method, which is a way of finding the volume of a solid of revolution. Our objective is we'll be able to write a definite integral that gives the volume of a solid of revolution that is obtained by revolving a region in the xy plane about a specified axis of revolution. So here's a problem that we want to look at. We have a region in the xy plane, and this region is bounded by the graphs of y is equal to the square root of x, y is equal to 0, and x is equal to 9. In this problem, the axis of revolution is the x-axis. So here's what we need to understand about this problem. If you look at this region in the xy plane bounded by the graphs of these equations, you have this region that's shaded here in the geometer's sketchpad drawing here. And we want to take this region and revolve it about the x-axis, and it will give us a solid of revolution. So let's first try to visualize what this would look like. To help us with that visualization, we'll draw a rectangle somewhere in our region, and you can see the one that's already drawn here. It doesn't coincide perfectly with the region, and it should not, because the top boundary of our region is a curve. It's not a line segment. So there is a part of the rectangle that actually goes outside of our region. But our purpose here is just to help us visualize what this solid of revolution would look like. So let's look at this rectangle that we see here, the red rectangle, and let's take that rectangle and revolve it about the x-axis to see what we get. So here's what we get. We get a cylinder, also called a disk. So now we're going to draw several other rectangles in our region in the xy plane that we want to revolve about our axis of revolution. And for each of them, we will go ahead and revolve each one about our axis of revolution. So we're going to get several cylinders that will approximate our solid of revolution. So let's take a look at these several cylinders that will approximate our solid of revolution. So here's one more, and here is the rest. Now you'll notice that in this particular drawing, the region that we have in the xy plane goes from x is equal to 0 to x is equal to 9. And what I have done for this particular drawing is I have partitioned my interval from x is equal to 0 to x is equal to 9 into 9 subintervals of equal widths. So each subinterval has a length of 1 unit in my partition for this particular drawing. So that's the partition, and on each subinterval of the partition, we drew a rectangle, we revolved that rectangle, and we got a cylinder, a right circular cylinder or a disk. And this is an approximation for our solid of revolution. So now how can we approximate the volume for our solid of revolution? We can find the volume of each cylinder and add the volumes of the 9 cylinders together, and that would give us an approximation for our volume of the solid of revolution. So we remember the formula from Precalculus, from geometry, for how to find the volume of a cylinder. You take the area of the base, and the base is a circle. So here's the area of the circular base, pi times the square of the radius, and you multiply by the height of the cylinder. And when you do that, you get the volume of your cylinder. So now we have to take that precalculus formula and apply it to our problem and find the volume of each cylinder, and then add the volumes of our several cylinders together to get an approximation for the volume of our solid of revolution. So you can take a look over here, and here's what we have. So again, we have our region in the xy plane, and we're going to revolve that region about the x-axis to get our solid of revolution. And we begin by approximating the volume of this solid of revolution using the volumes of several cylinders. So let's look at one of them in particular that I've drawn here. And we will find the volume of this particular cylinder by using our formula from geometry. So here's our cylinder, and we have to think in terms of the region that we have. So the volume of a cylinder is given by the area of the base, pi times the square of the radius, multiplied by the height. So let's look at the cylinder that we have and see how it's fitted in our region. So you see the cylinder, and here is the base of the cylinder, and here is the height of the cylinder. So what is the radius of this cylinder? What is the radius of the circular base? Well, it's right here. And again, you'll see the radius there. It's a vertical line segment that is in our region. How do you find the length of a vertical line segment? You take the y-coordinate of the top endpoint and subtract from it the y-coordinate of the bottom endpoint. That will give us the length of an arbitrary vertical line segment somewhere in our region. So now you see a total of 4 vertical line segments that I've drawn. The point that I want to make is this formula here is a general formula for any vertical line segment that is anywhere in our region. And we are able to do this because we know how to find the length of a vertical line segment. You take the y-coordinate of the top endpoint and subtract from it the y-coordinate of the bottom endpoint. Top minus bottom will give us the length of a vertical line segment. So now we do this generally, where we assign coordinates for the top endpoint and coordinates for the bottom endpoint using the fact that the top endpoint is a point on the graph of y is equal to square root of x. So when you have a point there and the x coordinate is x, y has to be the square root of x. And the bottom endpoint, it is on the x-axis. It is on the graph of the equation y is equal to 0. So no matter what x is, y will be 0. So now we take the y-coordinate of the point on the top and subtract from it the y-coordinate of the point on the bottom, and that gives us a function of x for the radius of an arbitrary cylinder that we have somewhere in our region, meaning this is a general formula that will give us the radius of a cylinder wherever it may be in our region, and the location is specified by the x value. So for a particular cylinder, you will apply this formula, and you will have pi times the square of the radius multiplied by the height. So this is going to give you the volume of a particular cylinder, such as the one that I've drawn here. The next thing is to recognize that to approximate the volume of our solid of revolution, we need several of these cylinders to fill our region from left to right, from x is equal to 0 all the way to x is equal to 9. And that's what you see here. You see a total of 9 cylinders from starting at x is equal to 0 and ending at x is equal to 9. And we can find the volume of each cylinder and add them together. So when we do that, we get what we call a Riemann sum. And that's what we have here. We have a Riemann sum here from I is equal to 1 to I is equal to n. So this is general, and of course if you replace n with 9, that means you have a sum of 9 products, each product giving you the volume of one cylinder. And each product is the area of the base multiplied by the height. So you can see that the delta x sub I is referring to the height of the ith cylinder. So this would be the first cylinder. This would be the ninth cylinder. Because I've done a regular partition, all of my cylinders will have the same height, 1 unit. And what you have here is the area of the base for the ith cylinder. And x sub I, you can choose it as I've done in my particular sketch here. X sub I is chosen at the right endpoint of each subinterval to generate my cylinder. So we've done this 9 times, so we have the sum of the volumes of 9 cylinders to give us an approximate volume of our solid of revolution. Now suppose you want a more accurate approximation. Now you can see that this is not the exact volume because our cylinders, each of them go outside of our region, so we have some extra volume. But maybe we want more accuracy. How can we accomplish that? Well, we can have a partition from 0 to 9 with more subintervals, each one having a width that's smaller than 1 unit. For example, you can have a partition from x is equal to 0 to x is equal to 9 with not 9 subintervals, but with 18 subintervals. And the width of each subinterval in this regular partition will be 1/2. And on each subinterval, you can do the same thing that we've done before, construct a right circular cylinder, and then find the volume of each circular cylinder and add them together. And of course, that gives us a Riemann sum. And you can see the upper limit of summation is 18 because we have 18 subintervals. And on each subinterval we have a disk or a cylinder. We have 18 cylinders. And this is giving us the sum of the volumes of these 18 cylinders. You can intuitively feel that this will be a better approximation than the one that we had earlier with 9 cylinders. Here we have a partition of the interval from x is equal to 0 to x is equal to 9 with 36 subintervals of equal width. So this is a regular partition, and the width of each subinterval will be 1/4 of a unit. And we can do the same thing that we had done earlier and construct a cylinder on each of our subintervals and find the volume of each one and add the volumes of the 36 cylinders. And that is represented by this Riemann sum that we have here, where the upper limit of summation is 36. Now let's take this idea to the extreme. We can consider what would happen if we continue to increase the number of subintervals. So I want to go ahead and replace the 36 with n. So now we don't have to have 9 or 18 or 36 subintervals, but we can have n subintervals. And we're going to let the number of subintervals approach infinity. So we're going to consider the limit of this Riemann sum and what happens when the number of subintervals approach infinity. Now I do want to make a technical point here. We want to do this in a way so that the width of the largest subinterval is going to approach 0. That is called the norm of the partition, because although we've looked at only regular partitions where the widths of all subintervals were equal, you could have a non-regular partition where the subintervals have different widths. So we want to make sure that the width of the largest subinterval will approach 0, and we call the width of the largest subinterval the norm of the partition, and we want to make that approach 0. So I'm going to replace n approaches infinity with this symbol here. This represents the width of the largest subinterval. It's called the norm of the partition, and we're going to make that approach 0. Now this implies that the number of subintervals n will approach infinity. So what we've done is we've taken our approximation to the extreme. And and we represent this as the limit of this Riemann sum as the norm of the partition approaches 0. So this limit will give us, if this limit exists, it will give us the exact volume of our solid of revolution by definition. And how do we know that this limit will exist? Because the integrand, well, first of all, before I talk about integrand, how do you represent the limit of a Riemann sum? Look at this definition of a definite integral. What is a definite integral? It is the limit of a Riemann sum, and that's what we have here. So look at this definition. What is a definite integral? It is the limit of a Riemann sum, and that's what we have here. So that's why we can rewrite that limit of a Riemann sum as a definite integral, because that's what a definite integral is. And how do you know that this limit will exist? It is sufficient for you to know that the function that you have in the integrand is a continuous function. So we want to observe that in our definite integral, here's our integrand. And where is that coming from? It's coming from this part of our Riemann sum, which comes from pi r squared in the formula for the volume of a right circular cylinder, giving us the area of the circular base. Now, where does this come from in our definite integral? It is coming from delta x sub I from our Riemann sum, which comes from the height of a cylinder in the volume for a cylinder, from the formula for the volume for a cylinder. Why is it dx? It is dx because when you look at our drawing, the height of a particular cylinder can be found by subtracting the x-coordinates of the partition points from our partition. And it is a change in the x-coordinates of one particular subinterval, delta x, giving us the height of a particular cylinder. That's what we have in the Riemann sum, and therefore we have dx in our integration formula. Finally, the limits of integration. You need to understand how you get the limits of integration. How do you get the lower limit of integration? How do you get the upper limit of integration? Well, you have to go back to your region. It starts at x is equal to 0 and ends at x is equal to 9. So in this particular problem, we will have the limits of integration from 0 to 9. So what is the definite integral that will give us the volume of our particular solid of revolution? The solid of revolution that is obtained by taking the region bounded by the graphs of y is equal to the square root of x is equal to 9, and y is equal to 0. Again, that's our region bounded by these three graphs, the green region. When we take that region and we revolve it about the x-axis, we get our solid of revolution, and as we have learned, here's how we need to write the definite integral for the volume of this solid of revolution. We take the square of the radius of a particular cylinder, multiply by pi, and multiply by the height, right? So we have our formula, and we use it to write our definite integral. Again, the radius is given by this function of x for a particular cylinder at whichever location it may be, and then we square the radius, we multiply by pi, and the limits of integration are from 0 to 9. So now we have developed something called the disk method for finding the volume of a solid of revolution that is obtained by revolving a region in the xy plane about a specified axis of revolution. Now when you have a horizontal axis of revolution, such as the x-axis, the height of each cylinder will be given by a change in x, so you will integrate with respect to x. But what if you have a vertical axis of revolution? So let's go back to our region from earlier, the region bounded by the graphs of y is equal to the square root of x, y is equal to 0, and x is equal to 9. But now we have a vertical axis of revolution, no longer the x-axis, but the vertical line, x is equal to 9, which is right here. So now we'll take our region in the xy plane and revolve it about our axis of revolution to get our solid of revolution, and we want to find this volume. So we actually are going to be using the same integration formula that we just derived, but now we have to apply it being mindful of the fact that we have an axis of revolution that is a vertical line. So what you should do is you should draw a representative rectangle in your region. And then you're going to see what happens when we take this rectangle and revolve it about the axis of revolution. So what you get is you get a cylinder or a disk. The important distinction to make here is that now our cylinder is oriented in this manner, and the height of our cylinder is actually given by a difference in the y-coordinates of two partition points we have in our partition. So the height is given by delta y, so our integration formula now is going to be with respect to y. We have to integrate with respect to y. It is the same formula, but we cannot integrate with respect to x, but we will instead integrate with respect to y. Again, how do you write your integrand? Well, you have the factor of pi and then r squared. You can factor out the pi because it is a constant. So now you need a function of y that will give you the radius of each cylinder. It has to be a function of y because we're integrating with respect to y. But what is the radius? Let's look at our drawing here. The radius is right here. That's the radius. I'll highlight it again using a different color, now green. That's the radius. And how do you find the radius here as a function of y? And why does it have to be a function of y? Because, again, you can draw different cylinders in this region. You can draw one closer to the bottom, and you'll have a different radius. You can draw one closer to the top, and you'll have a smaller radius. So the radius has to be a function of where the cylinder is located, and that is given by y. So you need a function of y that will give you the radius of an arbitrary cylinder, starting from the bottom, where y is equal to 0, and going all the way to the top of our region, right here, where y is equal to 3. So in this particular problem, the limits of integration will be from y is equal to 0 to y is equal to 3. And how do we get the integrand? You need a function of y that will give you the radius of an arbitrary cylinder. So the radius is going to be given by the length of a horizontal line segment. And how do you find the length of a horizontal line segment? You subtract the x-coordinates of the right and the left endpoints. That's how you find the length of a horizontal line segment. Again, look at how I labeled the coordinates of the right endpoint. It is on the graph of x is equal to 9, so x will be 9, and the y value is variable from 0 to 3, going from the bottom of our region to the top of our region. And look at the left endpoint. Look at how I labeled it. It is on the graph of y is equal to the square root of x. So if I solve for x here, I get x is equal to y squared. And y is variable. It goes from 0 to 3, from the bottom of our region to the top of our region. So now, how do you find the length of a horizontal line segment? Subtract the x-coordinates, right minus left. And when we do that, here's what we get. We get r of y is equal to 9 minus y squared. The radius of an arbitrary cylinder to approximate our solid of revolution is given by 9 minus y squared, where y tells us where the cylinder is, using the y coordinate, telling us where it is in our region. So now let's complete this problem by writing our definite integral. The volume is equal to pi times the definite integral. Now what is the integrand? we already have pi, so we need the square of the radius. The radius is given by 9 minus y squared, so we have 9 minus y squared, and then we have to square the radius. And then we have integration with respect to y. What are the limits of integration? Again, we're integrating with respect to y, so you have to look at your region. The y-coordinate of the lowest point is 0, and the y-coordinate of the highest point in our region is 3, and that's the definite integral that will give us the volume of the solid of revolution that is obtained by taking the region bounded by the graphs of y is equal to the square root of x, y is equal to 0, and x is equal to 9, and revolving about the vertical axis of revolution, x is equal to 9. In conclusion, we've seen how we derive the disk method to find the volume of a solid of revolution, and we've seen it applied to two different problems in which a region is revolved first about a horizontal axis of revolution and then about a vertical axis of revolution.